Today I'm going to talk about what we know about the nation's groundwater resources, focusing in on, I use the word reserves here for a reason, and that is because I'm going to focus primarily on the issues associated with depletion. I'll mention some aspects related to water quality along the way, but most of the discussion is more related to depletion. I'm going to talk about the nation at large, but in keeping with the spirit of their California Colloquium, I'll use a number of examples from California along the way. Okay. So any discussion of groundwater resources, one has to start thinking about sort of the units that one thinks about. And this is, groundwater is not a single pool underneath the Earth's surface, but instead is separated into a number of aquifers that are actually defined in many, many different ways at many different scales. But when one thinks about the nation at large, we've defined about 65 aquifers, major aquifers across the country in the Groundwater Atlas of the United States, which, by the way, is available on the web, and I've included the website down there if you're interested. And so I'll talk principally from that. Now, this map shows some of the problems actually with defining aquifers on a map to begin with, because what this shows is the shallowest principal aquifer, the uppermost principal aquifer for any given region. In some cases, some of these aquifers, like this brown area here shown, is the Floridan. The Floridan aquifer actually extends throughout Florida and the southeast, but it just happens to be covered by another principal aquifer over much of that region. So it's one of our challenges in groundwater is we're really dealing with a three-dimensional system. Now it's interesting because if you look at these major breakdowns, actually 20 major aquifers account for about 90% of the nation's total groundwater withdrawals. And the number one that shows withdrawals in million gallons per day, the number one aquifer is the High Plains by quite a bit. Number two, though, is the Central Valley aquifer system, and actually a couple decades ago the Central Valley would have been number one in terms of groundwater pumpage. It's being caught up rather quickly by the Mississippi River Valley alluvial aquifer, which is essentially a large floodplain deposit in the lower Mississippi River used in Arkansas, Louisiana, Mississippi, growing a lot of rice and other water-intensive crops. Very fast-growing aquifer. Number four, though, is an aquifer that actually exists within much of California. So if we look at the map again, we have essentially major aquifers in the Central Valley, the basin and fill aquifers in the southeastern part of the state, and then what we're defining as California coastal basin aquifers, which again are one of the major aquifer systems in the United States. So here in California, obviously, a lot of the major accounts for a lot of the groundwater withdrawals in the nation. Now, most of these colors are coded. The blue and the yellow are actually unconsolidated and semi-consolidated aquifers. And about 80% of the groundwater in the United States comes from unconsolidated and semi-consolidated aquifers, despite what all the karst people will tell you, actually. Much of the groundwater really comes from these productive sand and gravel aquifers. And about 2/3 of groundwater withdrawals in the country are used for irrigation. In California, that number's up to about 75%, about 19% used for public supply, and then maybe 4% each for self-supplied domestic and self-supplied industrial. So the big user is really, as everybody knows, is agriculture of groundwater. Now, there's a long-term interest in groundwater monitoring in the United States that really hasn't been lived up to. This is a quote from Oscar Meinzer back in 1935. In fact, there's a picture of Oscar Meinzer here surveying this is in San Bernardino County in about 1917. He and Doug Thompson were essentially mapping the desert water holes, if you will, so that the public in their new Model Ts wouldn't get lost on their way across the desert and run out of water. But back in 1935, you can see he was calling for a long-term nationwide program to essentially monitor the nation's groundwater reserves. We still have interest today, but it comes in rather odd ways sometimes. And this is the simplest way in which people might think about it. This was taken by another federal agency I might mention. I won't mention who. And they sent me an Excel spreadsheet. And what they had done is they'd taken our principal aquifer and they'd turned it into an Excel spreadsheet, and they wanted me to fill in this column over here, which was depleted, yes or no. So lots of times we tend to think of these systems as basic bathtubs, and they're either half full or 3/4 full. And so one of the points I'll make today, and most of you know this, is it's a lot more complicated than that. I never did fill out the table. If you go back, there's been interest in overdrafting of groundwater systems in the United States, even back in 1951. And most of it, as you can see here, is centered around California and the southwestern United States. I think what I have to do is quit putting my finger over the laser pointer here. So you can see in many of these areas, Antelope Valley, San Joaquin Valley, are all well known to you today. It's interesting, this little thing up here in Fessenden, North Dakota, that turns out to be a city that kept putting their wells into a nice, small, isolated sand and gravel glacial aquifer surrounded by till. And so they got to be classified as groundwater reservoirs with potential perennial overdraft. Now, some of this focus on the Southwest leads to a particular view by those outside of the Southwest and outside of California about Western water. This is a billboard. You can see the billboard here that was put up outside the airport for a meeting of the Great Lakes governors discussing about whether they would allow any water to leave the Great Lakes region whatsoever. And as you can see, you've got these stereotypes here. This is Michigan. These are the Great Lakes. They've got their straws, and it says, "Back off, suckers. Water diversion, the last straw." So I think they got their point across there. But of course, when you start looking at cones of depression associated, isolated cones of depression associated with groundwater pumping, even back in 1951 and continuing on today, you can see it's very widely distributed in terms of areas where there's a significant drawdown in groundwater levels. Back in 1983, in the USGS in the National Water Summary, we published a map that showed areas where water table or artesian water level decline were greater than 40 feet. And some of those areas are obvious to you today: Central Valley, parts of south central Arizona. This here is essentially the Dakota aquifer that was used that had large artesian pressure. I can show you. So that's the kind of wells they first had in South Dakota. That's about 100 feet of water shooting up into the air that they essentially used to power their flour mills and other sources of power until they ran out of artesian pressure early in the 1900s. So most of that depletion occurred a long time ago. This area here in the Milwaukee, Chicago area, and Silurian dolomite here in Iowa continues in some places to have large drawdowns and others to have a fair amount of recovery depending on where you are. We're currently in the process of trying to update this and make it more of a distinguishing between water table or artesian water level declines, because they're obviously very different in terms of significance. Well, we also have artesian wells, maybe not quite so spectacular, in California at one time. This is an artesian well in Lancaster, California, which is essentially in the Mojave Desert, about 1920, and it's an uncapped well, essentially wasting water. Today, this happens the same area, and here's essentially the city of Lancaster right here. These are contours of subsidence in meters from 1930 to 1992. So you've got about 6 feet of subsidence in that same area I just showed you, the artesian well. And it continues today. The shaded areas are subsidence from 1993 to 95, measured essentially by satellite, by INSAR. So you can see that it continues today. This is a crack in the nearby Edwards Air Force Base. This earth fissure I'm not sure if it was this one or another one, essentially shut down one of the runways for the space shuttle's alternate runways back in the early 1990s from subsidence from groundwater pumping. So subsidence is one of the issues that really one has to think about when you're thinking about, you've got a volume of groundwater, how much of that groundwater can you really use? Lots of times subsidence comes in to be the limiting factor, and I think that's one of the key points I want to make here today as I go through some of these examples is that long before you pump the last drop of water from the aquifer system, you're going to run into a particular feature that's going to be the limiting feature. And that's what I would call the myth of recoverable groundwater and storage. And I worry about actually, for example, in meeting the demand, some states have requirements, I think California does, for a developer to demonstrate that they have the water. Well, if that means that you go out and you take a groundwater system and you essentially look at the top of the aquifer and the bottom of the aquifer, and you come up with a volume, and then you multiply that by specific yield, that's a gross overestimate of the amount of water that you have available to yourself. And just to give you a couple examples here, let me back up. Houston, Texas was solely dependent on groundwater for many years. It's now undergoing a massive, very expensive conversion to surface water and groundwater because of subsidence. So they have a vast groundwater resource, but the subsidence is the issue that they're dealing with. The Republican River Basin is part of the High Plains in Colorado, Kansas, Nebraska. They've used maybe 3 to 5% of their 350 million acre feet of groundwater and storage, but they've essentially, base flow is about 50% of what it used to be in that basin. So they now have a moratorium on pumping. Edwards Aquifer, a few feet of water level change can essentially affect the discharge from springs downstream, essentially out of the karst aquifer. And the upper San Pedro Basin in Arizona that shows some of the development in that area essentially has used maybe 1 or 2% of their groundwater in storage, which is something on the order of 20 to 26 million acre feet. But yet they have a mandated planning effort to try to figure out how to reduce water. Fort Huachuca in the area is essentially on major water conservation practices in order because of concerns about surface water groundwater interactions. And the reason that is very simple. If you have a stream and it's not necessarily penetrating your entire groundwater system, and here's the land surface, the original water table, here's the height of the water table above the stream, you can see that you don't have to change on a percentage basis the thickness of your aquifer by a whole bunch in order to have a pretty significant effect on stream flow. So stream flow turns out to be, in many, many cases, the limiting factor to groundwater development more and more. And part of the problem is the subsidence is actually a fairly simple problem in the sense that you can come up with some reasonable estimate of how high, what you have to do in terms of your water levels. Basically, if you don't want to have inelastic compaction, you keep your water levels above the lowest level they've ever been before. Whereas surface water groundwater interactions is a lot more complicated. And it's not a problem, no, that people don't know about. I mean, many years ago, I remember I got a call from somebody at Science Magazine, I think it was, or Environment, a large magazine. They were doing an article on groundwater, and I think the second sentence out of my mouth was, well, you know, groundwater and surface water are connected. And the phone almost dropped out of the hand of the person that had given me the call because they didn't know that. But today, it's well known. I mean, the book by Robert Glennon, if you haven't read it, it's an interesting book about groundwater pumping effects on freshwaters across the United States. This circular here on groundwater and surface water is our best-selling technical document. It's even though we give it away free, but it's over 40,000 copies have been distributed. You can see the governor of Wisconsin in a State of Union address is talking about the need to protect groundwater, surface water resources, and he even got reelected after making this kind of statement. I don't know if that would happen here in California quite yet, but it did happen in Wisconsin. But the difficulty is that the time period and locations over which capture, and by streamflow capture, I mean essentially the combination of either reducing the flow of groundwater to a stream or pulling water away from that stream. So essentially, it's the amount of water that the stream would have had absent the groundwater pumping. And this is just a typical alluvial aquifer in the Southwest. It shows the time of 50% capture with distance for a pumping well and distance from a stream. 50% capture means that at that time, 50% of the water you're pumping is coming from the surface water body. Now, ultimately, all your water probably in this situation is going to come from capture. But you can see what happens is you get out to around 12 miles from the stream, and it's 100 years until you're actually seeing those effects. And you can play those, a better example perhaps is just to look, better example if it shows up, doesn't show up. Okay, well, I'll describe it. What this is supposed to show, maybe I can, there's an X here. There, no? Okay. What this shows essentially is a well pumping from the Colorado Plateau and its effect on some streams about 20 to 25 miles away, and a simulation in which there was 100 years of simulation, 50 years of pumping, and then stopped pumping for 50 years. And what you see is first of all, the water comes mostly, but not exclusively, from the nearest stream. So in other words, water will come from multiple surface water bodies around a particular area. Second of all, what you see is that the effects are spread out over time such that the amount of the depletion is very small, but it goes on for a long period of time. And the third thing is that actually you shut off the pumping, and the maximum effect of the pumping on the stream occurs decades later. So in other words, your maximum effect is not coincident with the termination of your pumping in a situation like that. Okay. So a lot of entities essentially try to deal with this term groundwater sustainability, which is really a societal term. And what that conveys is the idea that what level of pumping can we tolerate? What level of effects? Because if you're going to develop the groundwater resource, you're going to have some effects. If you're going to withdraw the water, it has to come from somewhere. And I like this diagram. It was put together by the Upper San Pedro Partnership. I mentioned the Upper San Pedro a while ago. And it shows essentially at some steady state, you've got cumulative change in groundwater storage. You have this much storage at some time. Then you begin development. You draw down your storage. Finally, at this point, you start to get worried. And you got to figure out what to do about it. Well, it doesn't make any sense to try to you're not going to get back here anytime soon, particularly if the recharge rate is changed on you, since it was much wetter, maybe during Pleistocene times when some of this water was recharged. But what you want to do is you've got somewhere between cessation of groundwater use and sort of leveling out here. And really, you've got a lot of choices, and it's a public decision-making process at that point to decide where between these two lines here you really want to develop your groundwater system. And they're very much struggling with that right now in the San Pedro River Basin. Okay, I mentioned, just because I don't want to leave it completely, most of what I'm talking about is groundwater depletion, water quantity effects. But many times those are intermingled with water quality. And there are many areas where, for example, first of all, the mere pumping of a well can induce contaminants to flow either from, in this shown here, a surface water source, or from a deeper, poorer water quality source, or from a contaminated water body. Interestingly, in our website at the USGS for groundwater, I've been told that the most common topic that people come to our site for is saltwater intrusion, which is obviously a very big issue in California along the coastal regions, continues to be along both coasts in the United States today. Essentially, the whole topic of artificial recharge, which is very much tied back into the sustainability of groundwater resources and how much groundwater you can use, is really tied into water quality issues. I mean, the major issues, there are certain water quantity issues, but really in terms of a water supply issue, artificial recharge is really, for the most part, a water quality issue. Second of all, I haven't said anything about climate yet, but obviously there's a lot of discussion about climate change in the western United States. Many of you have probably seen some of these. The whole question about red means less snow here. So less snow in the mountains, less spring snowpack, and earlier snowmelt runoff has obvious implications for operation of surface water reservoirs, but it also has implications for groundwater recharge, which are hard to get your hands around because we don't have the monitoring systems and because of the delays in the system, et cetera. But there's for sure going to be some change in the in-place groundwater recharge in the mountains, which may be very important from an ecological point of view, and also in terms of a lot of recharge takes place at mountain fronts, essentially water discharging from relatively impermeable mountain blocks into alluvial systems. And obviously there's going to be a change as there's a change in discharge there. So we're just beginning to try to get our handle around the climatic changes. Okay, what I thought I'd do is say a little bit about data themselves, since I started out with Meisner's quote. And there are places in the United States where we have nice long records, and this is what we'd like to see. This is a record for the Memphis area, which is almost totally reliant on groundwater, even though it sits alongside the Mississippi River. And you can see here, this is about 1930 here, up to 95 as far as this graph shows. But the bad news is there's this long, steady 70-foot drop in water levels. These wiggles are really not recharge, but more pumping induced, seasonal changes in pumping. But you can start to see it flatten out here. This is near the center of the cone of depression. If you get further east, this just keeps going. And essentially, the cone of depression just kept moving further and further east and probably continues to do so today. But this is the kind of data that we'd like to have everywhere in order to work with. Another element of it is we'd really like to know what that pre-development water level surface does. And unfortunately, people don't get interested in groundwater typically until they've been using a whole bunch of it. And so it's very difficult sometimes to go back and get the pre-development water level surface. So you have a basis for knowing how much groundwater you've depleted over time. This just shows contours. Fortunately, in this case, this is the Phoenix area. So Phoenix is right there, Salt River here. Contours of water levels in 1905 by W.T. Lee. So fortunately, we have that. Otherwise, we'd have these series of wells, the first of which, in terms of records, starts in 1929, well after the 1905 and well into the development of the basin. And if you point these dots out, but this is the kind of data we typically have. Many of you would know that. For example, here's a well in that same area. There's a 35-year gap between measurements. We could draw that line. That's easy to draw. Not exactly clear what happened between there. And then you got this one outlier out of 4 points. What do you do with that? Well, you can calibrate any model you want by picking the 2 points that seem to work for you. Fortunately, here, in this case, we had a well nearby that at least had some semblance of a record, although again, with an outlier. So we're dealing a lot with these kinds of records. But even if you don't have the pre-development surface, if you have some recent trends in groundwater level measurements, you can begin to at least see what the recent trends are. And this shows an experimental way of showing areas where there's falling, mostly stable, and rising in blue water levels in Arizona, essentially, most of Arizona there. So you can begin to get a handle on the situation if you get enough wells. And Arizona happens to have a pretty good network of wells overall compared to many states. It's very variable across the country. I should mention we don't only use water level measurements. One of the disadvantages of a water level measurement is you have to put a well in the first place. There are other techniques, for example, microgravity techniques with microgravity meter here that you can actually measure changes in gravity, which is shown on the left here, groundwater storage based on the microgravity data versus water level change based on water level measurements. And ideally, if you have them both, you can actually characterize the storage properties of the aquifer system. Now, the microgravity, it doesn't care whether that water is in the unsaturated zone or the saturated zone, but it gives you some sense of the volume of water in storage. And there are even approaches that now are, there's a GRACE mission, which is essentially monitoring gravity changes around the globe on a periodic basis. And they can distinguish changes in terrestrial water storage on the order of a few centimeters. But the problem is it's over areas like hundreds of thousands of square kilometers. So something like the High Plains Aquifer, it's nice to know what the change in water is over that area, but I think I've probably convinced you that most groundwater issues are really local in nature in terms of trying to figure out what the impacts are. Okay, I'm going to use a few examples here, but I want to just reinforce the idea that each groundwater system responds differently to pumping. And these are just simulations from our old RASA program around the country. And the red is changed. So each one of these pies shows where the water came from overall that was pumped from the aquifer systems. And the red is decreased storage. So most people might think there should be a lot of red in these circles because that's where obviously you pump groundwater is coming from storage. And it's interesting that some aquifers, that's true, for example, the High Plains. But in many cases, you're not getting any change, you're not getting much change in storage. And these are actually simulated as steady states. So the Floridan and the Edwards Trinity, you actually have a system that's not really changing overall in the long run in storage, but it changes on an annual basis in storage. And these are overall averages. The other interesting thing is the blue here is increased recharge. The yellow is decreased discharge from the system. And the increased recharge where it's coming from irrigation is hatcheted here. So what you can see is essentially that the large driving force on groundwater budgets that irrigation is in the western United States, as well as in some other areas, but mostly in the western United States. And so let me give you 3 examples of how these can differ. And I'll talk a little bit about the High Plains Aquifer in the central US, the Middle Rio Grande Basin Aquifer in the vicinity of Albuquerque, and the San Bernardino area in California. So the High Plains Aquifer, some of you may have seen this map, which shows depletion, water level change. Red shows the areas of very large declines. Most of that is in the southern High Plains, much less in Nebraska. But what's also interesting is you have to look at this as a certain scale, because this shows the change, water and storage in the High Plains Aquifer in pre-development and in 2001. You really don't see much change there in some of these states, and you can also see the dominant amount of groundwater that exists in Nebraska. So there's really overall, there's only been about an 8% change in groundwater storage in the High Plains Aquifer, yet we hear a lot about it, and there certainly are serious concerns about depletion in certain areas. One of the interesting things a number of years ago was the question about sort of incentives for irrigators. What incentives did irrigators have to reduce their pumping from the aquifer? And it depended a little bit in terms of how they viewed the aquifer system. If they thought about it as a bathtub, where basically they drew down the water and everybody came out of the bathtub and the whole thing went down, everybody's water was essentially the same, then there wasn't a lot, they might have some incentive. Most of them, but not much. Or if they thought about it as an egg carton, where it was a cone of depression and they had their own water supply, this is sort of their own private water supply here, if you will, then they might have more incentive. Or of course the truth is somewhere in between, and it really is in terms of how you think about it. So this is just a simulation pretending like we were conserved groundwater over a 10-year period over different management size areas. And then they ask the question, how much of that water that we conserved from not pumping remains under that same area after certain periods of time? So for example, this shows management area in square miles. So for example, after 20 years, you had 10 years of saving and then 10 years of still seeing how much of that water remained underneath your land. If you're at the size of a few square miles, like a typical farm might be, a small one, you don't have much of your water remaining. You really have, but if you get out to around 250 square miles, you got about 60% of the water you saved remaining under your land. If you get out to 1,000, you got about 80%. And so it suggests something about the size of management areas in which people actually banding together have some incentive to save water. And interestingly enough, in the high plains, in many of the high plains states, there are these water conservation areas in which they essentially band together and try to regulate the resource themselves. So it's very much a storage-dominated system in terms of the issues. The Middle Rio Grande is a little different. This shows it's a Rio Grande here. It's in the Rio Grande Rift Valley, which really goes all the way up to Leadville, Colorado, all the way down into Mexico. But the Middle Rio Grande is this area around Albuquerque from Cochiti down to Santa Casia. It's about 3,000 square miles. It's almost a large percentage of the population of New Mexico lives here, and Albuquerque was essentially sole source groundwater city for quite some time. Still is pretty close to that today. And what they thought and the interesting thing about Albuquerque is when they set up the city, they set it up above the most productive part of the aquifer system. And that was the part that got studied. So they just kind of extrapolated that out. And they said, and they had advertisements in magazines about how Albuquerque was water rich and they had enough water into the next couple centuries, so on and so forth. And they had a Great Lake under them, not just any Great Lake, but Lake Superior. And they advertised this. And then they started to find that they had large water, 160-foot drawdown of water levels in the Albuquerque area, and they started looking at the geology a little closer, and they started to find out that their basin really looked like this, which is what one would think of in terms of this kind of faulted type basin and range type terrain. The other issue is they thought they had a lot more recharge than they had coming from mountain recharge. And so, but one of the things this study did was essentially we gauged a lot of the mountain front recharge and found out that it was really distributed quite differently than assumed and much less. And also the key issue related to water rights is that is the river depletion in response to pumping, particularly in the Rio Grande, because they have certain water rights that they have to meet and they have to account for in terms of their water rights. So if you look at a water budget for the Middle Rio Grande, just as an example, at steady state, pre-development, you got about 130,000 feet of inflow and the same amount of outflow. So it's the same for steady state, basically steady state, a little bit of error in the system here. But then if you look at 1999 as an average, what you see is all of a sudden you start to see you have a lot more inflow and outflow in terms of the system. You've got some change in storage in response to this pumping. And you've got a very dynamic system here between the Rio Grande, which now is essentially used to just lose water to the aquifer and to ET, and now loses a lot more water, but a lot more of that just comes back from drains that are on the river. So you have a lot, when you're starting to track your water rights situation, you've got a lot more complicated situation here in terms of thinking about, how much water are you really taking out of this river and how much are you recharging back into the river. So the situation here in Albuquerque is much more one of concern about the interaction of the groundwater system, characterization of the groundwater system and its interaction with the surface water body. Finally, the San Bernardino area, many of you are probably familiar with. So this is a valley fill aquifer down near the city of San Bernardino, Redlands. They're really lucky down there. They got the San Andreas Fault on one side, and they got the San Jacinto Fault on the other side. So it's kind of like having a Hayward Fault run through your campus, I guess. But they also have some rather large plumes to deal with in terms of water quality. But essentially, the city of San Bernardino is built on a former marshland. You have a lot of water moving down here. You had artesian conditions, like I showed before, in this area, which have since been depleted. You had a lot of groundwater pumping, and then you had less groundwater pumping, and you started to have water levels coming back up to the land surface. A whole different story here, because essentially what you're doing is you're creating a seismic risk because of the way in which the groundwater system operates, and you want to pump enough of that water in order to reduce the seismic risk. So it's again, just another example of sort of a much different system, groundwater system, in terms of how you think about it. This shows just a water budget that was done for the system with a bunch of different components. I think a key point here is that there's recharge in a number of different ways and discharge in a number of different ways, which are calculated outside of a model. And then there's a change in storage. This is an average over several decades. It's only a 4,000 acre feet per year, so it's relatively small depletion, but these numbers don't add up. So your recharge is 174,000, your discharge is 200,000. You should have essentially 26,000 more here, and you're only accounting for 4,000 of it in the change in storage. So essentially what they have gone back in this particular study is to go back and look at other inferences to try to fill in that uncertainty that you have in your water budget. And I think that's the key point here, is that any of these, even these gross water budgets for large groundwater systems, have considerable error associated with them. And for example, there's an adjacent basin right here that has a model for it that suggests there's a lot more water coming across the San Jacinto Fault than they had anticipated in this particular study. And so that's one of the terms that's showing here. There's also some land subsidence that hadn't been accounted for. And there's also some bedrock seepage. So there was actually a study done of heat that suggests that there's actually more water coming through these relatively impermeable mountains than was anticipated by the original calculations here. The other interesting thing is, remember I told you there's only 4,000 feet of change of storage over this 20, 30, 40-year period, but the change in storage is dramatic on an annual basis. So in other words, basically what happens here is they get most of their recharge maybe every 5 to 10 years with a major precipitation event or wet year. And so you see these spikes, and this is change in storage in acre feet. They have literally hundreds of thousands of differences in storage in the aquifer system just on an interannual basis, just because of the way in which the system operates. So again, it's sort of, you have to think about the water balance in a temporal point of view, even for a groundwater system. Also, it's not just a simple average annual type event. Okay, finally to mention just a couple things that are ongoing to try to deal with Oscar Meinzer's question. First of all, since January of this year, there has been formed through sort of a federal agency, the Advisory Committee on Water Information, a subcommittee on groundwater that's essentially looking at the questions associated with what would it take to have a national network of groundwater wells for the country. And it's basically an effort between a number of different agencies you see there, and the National Groundwater Association is very heavily involved in this effort also. The other thing I think I've hopefully conveyed by now is that monitoring alone doesn't tell you what you need to know. You've really got to have an integrated monitoring and modeling effort ongoing in order to deal with questions, for example, the surface water questions. Changes in water levels are not going to tell you what might be in store 10, 20 years from now in terms of stream flow depletion. You really got to take that water level information and integrate it with your modeling exercise to answer those kinds of questions. And so if I just consider an ongoing monitoring program, and initially you have a model, you adjust your monitoring network based on that initial model that gives you some guidance, and then you periodically come along on a decadal basis, ideally, actually, and update your conceptual view of what that groundwater system looks like. And I pointed out in the San Bernardino area how, for example, in that water budget, they may have had some things wrong with their conceptual view of how water moved through that mountain block or how it moved across faults. The simulation model adjusts the monitoring network, and this is sort of an iterative process. Now, this almost never happens, unfortunately. But there's probably no better time to think about a monitoring network than when you've just gone through the process of putting all this data into a groundwater model and running it and knowing what, having a sort of some sense of what the uncertainties are and where your gaps are. And then other data, of course, come along like environmental tracer data, that geologic and hydrologic studies that probably, above all, influence your view of the conceptual model. For example, you may have age dating carbon-14 or tritium or otherwise that your model doesn't reproduce. I mean, you can use your model to estimate the time of travel to your points of sampling, and if it's way off, that suggests that maybe there's something wrong there. So that's the ideal, but we're not going to get there anytime soon. We also have a program that we've begun looking at some of these large systems, trying to weave it into a regular type assessment. And we've undertaken studies beginning essentially beginning in 2004 in the Central Valley and Carolina Coastal Plain and the Denver Basin. And then we're adding one a year at the moment, some of the major systems across the United States. So to try to do essentially water budgets for these systems, estimates of trends in groundwater storage, recharge, and discharge, provide these models that can provide either a context for more local studies or can be used in a predictive case for the larger system. And also trying to address this question here, which is to take a look at the monitoring network and make some statements about the adequacy of that, as well as to look at new approaches for analyzing these types of systems. So if I can just summarize, I've tried to cover a number of different areas of how one thinks about assessing or evaluating our groundwater reserves across the country. Hopefully I've convinced you that it's more than just calculating the amount of water in storage and dividing it by the number of years you want to have the resource available to you, and then you know your pumping rate or your consumptive use rate anyway. But we have some ability to track groundwater conditions for many aquifers in the US. We have a more limited ability, I'd say, to place it in the context of groundwater sustainability, which is really a societal concept anyway. The dynamic response to stress and associated issues of concern vary greatly among different aquifer systems. All aquifer systems were not created equally. They're very different in terms of how they respond to pumping stresses. And that the ideal approach has an integrated approach that has a feedback among monitoring, simulation, scientific studies, and for that matter, management approaches in order to try to design the best system to look at groundwater systems over time. You really need to try to pull all of those elements together in a common framework. So I think that does it. Okay, I'll try.
You talked about a societal concept of moving towards sustainability, but what happens when science is privatized and you have an administration that is at war with science? And how reliable is any of this stuff given the ownership? You talked about water rights situations being very different. And
Yeah.
It seems to me that the public trust doctrine says that water is essentially public, and the rights, are recognized subject to that public trust. And yet there wasn't much talk about public trust in
Yeah. So the question is basically one of, can we trust the government, I think, to provide the true facts for people to make decisions by. Or private enterprise.
People who have just absolutely direct conflicts of interest, which nobody seems to worry about.
Yeah. I can't speak. First of all, I work for the administration, although that doesn't reflect my party affiliation. I can't speak for offices of communication for particular agencies that have a vested interest in a particular decision-making process. But I've always been, I almost never have come across a scientist within the federal government or otherwise who doesn't really say what they think and sort of let the facts speak for themselves. So, and there does sometimes there is a conflict between the scientist's point of view, which may be different. I mean, it may be an individual scientist that has a much different view from a whole bunch of people over here. And sometimes it's been shown that that person was right and these people were wrong. But I've found that in terms of the scientific process itself, I don't think that that has been affected at all by any of the, and every administration has its own particular pet issues. And they do try to manipulate things, certainly in certain cases, I'm sure. But I would say the scientists themselves are our best bet there in the terms of they don't want to, and you hear that all the time. And sometimes it's legitimate and sometimes it's not, but it's vented anyway. I don't know about, I've spent 30-some years working for the government, so I can't speak to private enterprise, but my experiences with the limited people I've had to deal with in private enterprise has always been very positive on a one-on-one basis.
But the government try to privatize and make competition between the USGS and private companies?
We have there's certainly, and particularly with this administration, there's been lots of issues about privatizing certain things that we do. For example, we just went through a recent exercise evaluating our National Water Quality Lab in Denver and whether that should become a private enterprise or not. Fortunately, at the end of the day, it was just decided about a week ago that it would not, although there's still a process of questioning that, perhaps. And so there's and weather service at times. There was an idea, somebody's bright idea to privatize the weather service at one point. So I'd say there certainly are people and entities out there that very much think that if you're a government employee, you must be down here, and you're not really an American. We want to fund somebody over here as in private enterprise, but those will always exist. So far for our agency, I would say we're pretty much of a science agency we pretty much do most of the science ourselves. We fund out, we do contract out certain services, but not many, probably to a fault, actually. We probably don't have enough interaction with universities and other entities, for example. Yeah?
Are there any other countries that are doing interesting work with the feedback monitoring that you were talking about, wishing there was more of in the States?
It's really an area that I think is relatively unexplored. I think that I've seen, I think that some countries like France, for example, have a number of different experimental areas where they're very much integrated in their groundwater, their data collection and their data processing or data simulation type exercises. So it's probably as hit or miss elsewhere as it is within the United States, I'd guess. I haven't seen, it's kind of an unexplored area. Maybe because it actually is very difficult to make statements about monitoring because it's so dependent on your objective. It's like an optimization problem. It's dependent on your objective function and your constraints. And so, like any network design problem, most natural science data are used for multiple purposes, so it's difficult to do it real hard and fast and quantitative without making very specific assumptions about what those objective function and constraints are. But nonetheless, I still think that you're going to have some very obvious things that are going to hit you right across the head when you're trying to do a modeling study and you find out you've got, and you're going to identify, for example, records that you've gone through a lot of work to identify as being reliable. It may be a well, you know you've got good construction information, you've got good information, you've got a good geophysical record to go with it. All that kind of stuff should be feeding back up into sort of the decision making related to monitoring networks.
Is the Ogallala Aquifer essentially the same as your High Plains data? And two, the second question, in Wisconsin, the lakes, the municipalities close to the lake draw on Lake Michigan. And there's frequent rain. What's the problem there?
Okay, let me take the first one. Is the High Plains and the Ogallala the same? Almost. The High Plains actually include, the Ogallala Formation is the dominant formation in the High Plains, but there are other smaller geologic units that work together with the Ogallala to form the High Plains Aquifer. Okay. The second question is, what's the problem in the Great Lakes area in Wisconsin? Yeah. Well, first of all, there's a precedence. There's a huge concern with precedence about moving water out of the Great Lakes and to anywhere else. Whether one drop is a precedent as far as they're concerned. And the Great Lakes are a little bit like, they have 20% of the fresh water on Earth, I believe, something of that sort, some amazing amount. But they're a little bit like groundwater situation I described. That is, if you could pull the water out of the bottom of the Great Lakes and the top wouldn't fall down, then that would be great. But essentially you have a lot of interests that have all adapted, both environmental interests in terms of wetlands around the Great Lakes, as well as human interests in terms of where people have their docks and erosion and issues like that, that really make it so that the Great Lakes is very much, they will tell you we're using all the water in the Great Lakes already. There's not a drop to go elsewhere. The reason the groundwater pumping in Wisconsin started in a big way, I believe, was because of water quality concerns. I think it started in the late 1800s, and there were cholera epidemics and concerns about essentially bacterial contamination of water coming from the Great Lakes. And so they turned to groundwater in a big way. And then they got themselves in a situation where they were, everybody else has spoken for the Great Lakes over here, and they're trying to reduce their pumping of groundwater. And there's a considerable controversy in the Great Lakes region, and particularly in Wisconsin, about whether you're pumping groundwater, is that water coming from the Great Lakes, or is it coming from from elsewhere? And it's not an easy question to answer because it depends on what aquifer you're pulling from. And also that line, if you can think of it like a topographic divide, has changed over time as pumping. As you start to pump, you start to move that line in terms of where that divide is. So they have it's almost like California all over again in terms of debating about water resources in that whole southeastern Wisconsin area. Yeah.
You have a citation for your 2006 ideal model for monitoring?
Oh, actually, because I needed to get rid of some reprints, an article by the same title of the talk I gave, which is a little different, actually has that in it. Is at the back, there's a stack of them at the back of the room, at least there was, at the top there. Or I have a copy if you need one. The question was the reference to that diagram I had about integrated monitoring and modeling, where that came from.
Well, what you presented seemed like these bodies of water were very static, and to me they're always moving. So I would, in my own thinking, would like to know, do you integrate any of the geologic stuff about seismic events into the modeling?
Okay, the question is, the presentation made it seem like these bodies were too static as opposed to moving, and then do we integrate seismic? So by moving, you mean shaking, like in seismic shaking, or in terms of moving in terms of flow paths?
Well, flow paths.
Okay, yeah, so let me answer the first question. I think, hopefully I was trying to convey, and it's tough, I probably should have a movie or something that's sort of a dynamic picture to convey the idea that groundwater systems are a lot more dynamic than people tend to think of them as. And that's what I was trying, although that may extend over decades in terms of the way you think about it, but they are constantly changing. In terms of seismic, well, I illustrated the seismic issues down in San Bernardino very much tied into groundwater. We actually, within the LA basin, we have had a long-standing study between the earthquake folks in the USGS and our groundwater folks, because we have a lot of common interests in terms of defining the geologic framework. So understanding more about those faults and the geologic framework and the characteristics of the sediments, obviously, is of great interest to people interested in earthquake hazards as much as it is to people interested in groundwater. So there's a lot of overlap there.
It's my understanding that there's very little groundwater law in California. And would you recommend, or do you think that implementation of the water rights as a public trust is in order in California, unlike, say, Colorado?
Yeah, I'm probably not qualified to answer that question. Probably the answer is yes. The question is, should California have more groundwater law in terms and regulations in terms? Should it take just simply getting to the point where you have to educate a basin to get to the point where you're starting to try to worry about how people's water rights are impinging upon one another? And I would say, obviously, my answer to that would be groundwater is a very important resource to California. And so as a groundwater scientist, groundwater hydrologist, I would think that I would tend to weigh in, obviously, on more regulation, understanding of the system. As a federal government employee, I can't get into the business of state government, though, so I'm also not really qualified to answer the question, get too deep into that. Yeah?
I was wondering, because in surface water we have sometimes effluent-dominated streams and rivers. And I just wondered, through the data that you've looked at nationwide, if you've come across any groundwater aquifers that have been effluent-dominated.
Mostly most of the cases that are well known are in California. For example, from the water quality sampling that was done from our National Water Quality Assessment Program down in the Santa Ana River Basin, the groundwater system down in Southern California. If you look at that shallow groundwater system, you see essentially, and you can see it when you look at it, they recharge up in the higher areas, and you can actually watch the age of that water. Then by tritium dating, by looking at the volatile organic compounds in it, you can see where essentially humans have displaced a very large percentage of the groundwater in that basin. Now, I suspect there are other areas of the country, and it just hasn't been looked at in that way, where, in effect, humans have displaced the old and put in the new. And of course, that's a big issue in things like recharge and so forth.
Other than Santa Ana, then you're saying you haven't seen that?
I haven't seen it presented in that way, but I suspect if you looked at very intensively used systems, certainly in Orange County, I would think, again, in California, very intensively used system, you're going to see that essentially we have, and particularly where we have the large recharge operations in place, you're going to see that we have had, we've displaced the old natural water, if you will, with essentially human-introduced water. Question?
You talked, and it's a fascinating thing about how the surface water is so much more a part of the groundwater system. And, like the Great Lakes thing. But also in California, getting back to this law question, the law has treated groundwater separately from surface water. As a scientist, does that make any sense whatsoever to you?
No.
Okay. That's interesting.
And I think it's coming to a realization. And it's tough because you have this long history of essentially property rights that have been based on that system. And it's hard to undo property rights.
So as a scientist, do you find them listening to you?
I think that it's hard to argue anymore that you didn't know. Okay, so I think most everybody that works for state agencies that are involved with water is aware on some level that surface water and groundwater interact. There are a number of states, and there was just a big TICE conference for the National Groundwater Association on this very topic where they brought experts from each state. Each state is dealing with that very differently, all the way from nothing to states that are very proactively, I understand Idaho is one of those states, very proactively trying to work their way through the system and kind of ultimately get it right. But because it's so embedded in a property rights system, it's tough to unravel.
But the Idaho legislature abolished its public trust doctrine with regard to the Snake River. I mean, does that reflect a state that's really...
Yeah, again, I'm only reflecting on sort of the conference proceeding, and more recently they have a number of people that are thinking hard about the problem. I can't speak to the specific, because I don't know the laws in each state, what they're doing. But I mean, it's not hard to look at most states and say that you're right. They have a long history of treating the two as separate, and it's taken a long time to even admit that they are connected. I think we're now at the stage where we're admitting it. Now we're trying to figure out what to do about it. Yeah.
So the monitoring and measurement, I'm assuming the obstacle to getting it into place is financial, and I was wondering if you could speak to the funding.
Sure. You know, there's a lot of concern about data, hydrologic data or meteorological data. And some data gets more interest than others. For example, the meteorological data, everybody knows that they need it for weather forecasts, and we're all paying attention to the weather, and so it gets a lot of attention. Stream gauge, we find that there's almost a movement for more stream gauging data in the country. There's a good recognition that we have a paucity of data, and what happens there is you have a tragedy in the sense that somebody removes a gauge that might have actually saved some lives, as they find out later, or you have big flooding and people suddenly don't have the information they need, and so on and so forth. Groundwater is actually is probably the hardest data to argue for, because there's no event that really triggers interest in it until either the well goes dry, so to speak. So it's tough to argue for, and it's very distributed around the country, and so that's what this one group at least is trying to try to come up with a little bit more of a push for groundwater data, because we've seen a decay overall in many areas of the country in terms of groundwater, basic groundwater monitoring. Yep.
Would that be a function of lack of funding?
Yeah, but is it a function of lack of funding? Yes, I would say very much so. And priorities. It's a question of priorities.
Can you see a future for more funding or less funding to continue gathering this data?
Usually what happens is interest in groundwater data manifests itself by droughts. So when you have a major drought, then you have major interest in groundwater data. And if that drought happens to occur in Washington, D.C., you really have a lot of interest in droughts, because there was a drought while I was there in Washington, D.C., and that's the closest we ever came to getting a sort of an expansion of groundwater data collection in the United States. So hope for drought in the East, not in California. Oh, yeah, sorry.
So I understand that the surface and groundwater systems are very much connected. What I'm wondering is, if I were to pump an acre foot of water and I have a relatively inefficient application on my field, and a quarter of an acre foot then runs off, how much of that makes it back into the groundwater, and how much of it ends up running off and being lost?
Okay, so the question is, if a person pumps an acre foot and they have a field you're irrigating or something,
Yeah, they're irrigating.
and it runs off, a quarter of it runs off. Yeah, it all depends on, what you're talking about is what's known as consumptive use, which is the question of how much of that water is actually used.
Right, but that portion of it isn't being productively used.
Right.
Does it all make its way back to the groundwater table? I mean, I'd like to think it did, but I have a hard time believing.
Probably not. And there are interesting situations that arise because you have big systems that are developed over time that, for example, are very inefficient, but suddenly you have systems that are dependent upon them, and all you got to do is look to the Imperial Valley in Southern California, where you have these very leaky canal systems that essentially are maintaining flow of water to the Salton Sea, or maintaining the flow of water to the wetlands in the sort of the border region between the United States and Mexico. So there's almost an infinite number of ways of what happens to that water that runs off, and whether it gets back to a groundwater system or not. And it all depends. Some of it depends on scale in terms of your particular interest. So, for example, in the Great Lakes region, their interest is sort of if it's going back into the Great Lakes drainage or if it's not, and that's their interest. So it all depends on sort of where you sit on the landscape in terms of how you think about that problem. Yeah.
I have a non-scientific question. Why is an artesian well called an artesian well?
I wish I knew the answer to that. I should know the answer to that. Pardon? Is it named after a city in France? Okay, there's your answer. There's a city in France. Must have an artesian well. And they copyrighted the name. Yeah.
I know that injection wells are often used to sort of get rid of wastewater and put it down into the groundwater aquifers. And I'm wondering if you know of examples where injection wells are being used positively to basically to bank groundwater or to recharge the aquifers with high quality water.
All over the place, particularly in California. What you're talking about is known as aquifer storage and recovery, which essentially is where you use the same well to inject water into the groundwater system and then pull it back up later. And there are many of those going up around, particularly California. Arizona is very busily banking water from the Colorado River that is not being used quite yet. Also in the southeastern United States, Florida is also very big in that area. Another interesting application is essentially which very much relates, is the whole issue of carbon sequestration, which is this whole idea of injecting essentially carbon dioxide into deep aquifers and hoping it stays there.
So what kind of rates can they get on the largest of these wells?
The injection wells?
Yeah.
I don't know. Do you know the answer? Somebody know I don't know the answer to that. They can do pretty good amounts of water. It all depends on, there's a whole maintenance issue associated with keeping them from clogging from either iron deposits or and things can happen because you're typically injecting a water that has a very different chemical characteristics than the aquifer you're injecting it into. So if you're in one of those situations, you can essentially create this chemistry that precipitates out material, or you can dissolve the aquifer and create an even more permeable aquifer in some cases. But I don't know the actual magnitudes of the large systems. Fair amount of water, though. Yeah.
Are there any classic examples of unforeseen consequences?
Are there classical examples of unforeseen consequences? Pardon?
In this area.
Well, subsidence was one. Certainly was a big surprise to people when they suddenly discovered they were having these large subsidence structures. Unforeseen consequences in this area. Well, I mean, it depends on what you mean by unforeseen consequence. You don't know whether it's foreseen or not. I mean, you got your whole delta region here that subsided and sitting there vulnerable to seismic, hazards. I don't know if that was foreseen or not. What that subsidence was, the amount of subsidence that was going to occur there and what the implications were. Certainly, a lot of these issues develop over time. It's not like all of a sudden it's a big, so a lot of these issues like the surface water, groundwater issues probably weren't thought about until a drought comes along and the base flow, you're wondering about the base flow and is that pumping having effect? And so typically, these are these various effects of groundwater systems, and they typically take you a little bit by surprise, I would say, in most cases. Maybe not in the big way you're looking at, but most groundwater problems kind of manifest themselves slowly. Yeah.
Do you have any knowledge of the little aquifer we have up here in the hills that hasn't been studied very much, the Leonard Aquifer?
Do I know anything about the Leonard Aquifer? Don't know a thing.
It's been pumped for 31 years now. In the parking lot of the Math Science Building on the hill, they pump it, and then they dump the water in the north part of the Strawberry Creek. It used to go in the south side. And it's supposed to, it's pure water, and it's supposed to be a possible drinking water bank. We just haven't done the politics on that yet because it involves the land, the city of Oakland, and so on and so on. But it's supposed to be very pure water. But it's a little one, and we don't even know, how far it goes into East Bay Regional Parks and what are the parameters of it. So how would we maybe find a way to designate that?
Designate, you mean characterize it, or?
Well, just like get it on the scientific maps. I mean, your stuff is pretty grand.
Right.
Scale. This is a little local one.
Well, you do have a university here. You ought to. Right. Must be a grad student out there somewhere. Is that it? One more question?
How critical is a drawdown of fossil aquifers?
Well, a lot of the water you see in terms of depletion in the Southwest is essentially, how serious is the issue of fossil groundwater? In large parts of the world where groundwater is intensively used tend to be arid, semi-arid regions. So depletion of essentially planned depletion in some cases of fossil groundwater is a big issue worldwide. Within the United States, I'd say within the southwestern United States, you had a lot higher recharge, at 20, 30,000 years ago than you have today. A lot of the water that's being pumped is old groundwater, tens of thousands of years old. So it's really more a question of what's your source of replenishment for that water. Is probably the bigger issue than the actual age of the water itself, because you may be able to replenish it either through artificial means, or you may be inducing flow from a surface water body or whatever that's replenishing it.
Thank you, Bill.
Okay.